And first of all, I would like to acknowledge my co-authors, Jordan Santillo, Robinson Wallace, directly working with me in the science team, and Pekka, Puhakka, and Juha Salmivaara from our weather radar research team. And yeah, in the wrong window. Let's see. Yeah, no, okay. So the content of my talk, first a short introduction, then of course description of the method, giving some examples for this, and then specific application where we actually already use this method in the quality assessment of one of our research weather radars, pre and post a magnetron replacement, looking at ZER calibration, and then the more general data quality assessment, some conclusion and outlook, and summary, of course. So monitoring the quality of weather radar data, of course, is, as we all know here in this room and online, is really crucial for many things. If we look at observations that are really crucial for the safety of lives and kind of avoiding damage to property, then of course the quality must be good. These observations must be reliable, and the derived products must be as good as possible. And so it's always important to know about the data quality of the data or the observations going into all these things. But also this information then can be used subsequently to look at the quality of derived products, which, for example, is what weight is given to observations when they are ingested into numerical weather prediction models. On the other hand, monitoring the data quality of weather radar observations can help providing an access on an opportunity to, instead of having a rigid maintenance schedule, having a more flexible schedule that is based on the quality of the observation and the quality of the individual radars. So that's one potential approach that might help cut costs and have a more flexible approach to maintenance, but also it could be in the future supported by artificial intelligence and machine learning methods looking into this aspect. So we have been looking for assessment methods that are nearly exclusively using weather radar observations, nearly because one observation that is currently going into the method is an external information about the melting layer height. You will see later why. Of course, there are alternative reference sensors, for example, the Vaisala FT70 forward scattering sensor, which Marjan Mabuti, my colleague, hopefully will present about on Friday. If she doesn't make it here, then I will get this presentation. But in general, not always. There are alternative or kind of complementary sensors around. So the idea was, what can we do if we only have these weather radar data? Also, how can it be done without an interruption of the operational observation? So a bird bar scan, for example, a very good method in light rain or general in rain to calibrate your ZER, interrupts your normal operational mode. So that is something you do not want to do too often. And external weather radar calibration even more so, because it's not just putting your radar beam to a different direction. It's kind of taking your radar out of the regular operation even for a longer time. So the operations we have, or the observations we have used here in this for this approach is we have 3 different research radars we use ourselves, and we have under our own control, which is an magnetron WRM at Caravar, which is about 10-15 kilometers away from our headquarters. Then we have at Helsinki University at the Kumpula site, we have a solid state WS300. These both are C-band radars. Then we have at the roof of our headquarters, we have a WS400, which is an X-band radar, solid state. And then we also, thanks for that, Anna Kaiser, by the way, we also have we had some observations from the operational FMI radar at Wichti, which again is an WM magnetron 200 C-band radar. And the examples I will show later here in this presentation are all created using Python code. So the method is pretty straightforward. So far, I'm always looking at a single scan. So I have not yet gone to the point where I sum up data from multiple scans, but looking at a single scan, the first point is to identify melting layer height and only use data that are closer than the range at which the radar beam reaches the melting layer height. So of course, to get a lot of data, preferably it always should be the lowest elevation scan. Then mass data for the radar reflectivity. So typically I'm looking at just using data between 10 and 20 dBz, so really a moderate range. There have been applications also customer demanded to look into 20 to 40 dBz, which is already, okay, let's say 10 to 20 is light rain, and 20 to 40 is then already moderate rain, which of course always gives you a bit of an impact from slightly higher ZTR values and slightly bigger drops. Then in addition, just to get rid of all kind of outliers, insect and all that nasty stuff, mass data for ZTR as well. So typically to get enough statistics, I'm currently using ZTR smaller than 0.5, ZTR plus minus in the range between plus and minus 0.5. But of course, when you have a lot of data, you can apply a more stringent masking, even let's say plus minus 0.1. Yeah, that's a matter of simply statistics and getting enough observations and enough range gates with data in this range. And then from this, calculate the statistics and fit theoretical functions. And this theoretical function that is now purely empirical and kind of based on my experience with how different size distributions look and what function could be used to fit them. So for the correlation coefficient rho HV, I'm using a kind of reversed log normal function, which is given here by this function here, by this formula here, where the input variable is the inverse of the rho HV. So rho HV runs between 0 and 1. So my x that goes into this function here, and that's why it's a reversed log normal function, is then going from 1 minus rho HV. So from 1 to 0 in this approach. For the differential phase, I'm using a stretched gamma function, which is following this function here, where the input variable is actually the measured phase, the measured differential phase minus the location of the maximum of the distribution plus 10. So that eventually shifts your whole observation, because your differential phase is depending on the setup of the radar and might be anywhere, theoretically, anywhere between 0 and 180. But I shifted now so that it is the resulting value is then between 0 and 20. And then I fit this stretched gamma function to this, and looking at an amplitude factor, stretch factor, and these two parameters here are the shape of the gamma function, the shape parameters. And so these are examples. So left side, right side. Left side is this is the rho HV with the stretched gamma. With a reversed log normal fit. This is these both are created from the same set of observations, but this is for set H between 10 and 20, and this is between 20 and 40. So in this case, the results are not really very, very different. And also in this green line here gives the cumulative contribution of all data between 0 and 1. So you see that the cutoff here is 0.96. And you see at the cutoff point, the cumulative contribution is here, the axis here is in the right side. So only less than 0.1, or so less than 10% of all data in this context here between 10 and 20 dB set for the reflectivity are contributed by rho HV lower than 0.96. And so this here is the peak maximum, which is also in both cases here for 10 and 20, between 10 and 20 and 20 and 40 is very similar. On the right side is an example for the stretched gamma fit for the phi dp for the differential phase. And again, there is, in this specific case here, there is not much difference between ZH 10 to 20 or ZH 20 to 40 dB set. There are other cases, but this one here is really, it wouldn't matter. So if you need more statistic, you could just use all data between 10 and 40 and just get a better statistics, but this is not always true. So just a caveat. There's an alternative function that I can use for phi dp, which is a Lorentz line or Lorentz function. So Lorentz function following this slightly complex function here is a function that is more narrow than the Gauss function. And I found that for very narrow phi dp distributions, but also for typical ZER distributions in the absence of very high ZER values in the observation, this is a much better fit than a Gauss function. So that's why I decided as an alternative for very narrow distributions, the Lorentz line or Lorentz fit, Lorentz function is a good fit. And this is one example where I looked at ZER and located the location or the kind of assessed the calibration of ZER without using a birdbath scan. A bit more about that later on. So a few more examples here. So as I said, the method has been implemented in Python. I'm using the PyArt package as one package in this, which this is the reference for this if you're interested in this. So we have observations, as I already mentioned, from our 3 research radars and from the Wichti FMI operational radar. One caveat for the data you will see in the next slides, which is unless the Wichti operational radars, our weather radars, our research weather radars are not in the first place operational radars, they are test beds. So we are testing things with it, we're playing with it, we're using methods. So the data quality is not necessarily always kept at a level of an operational radar because we are just doing things and just testing things that will probably not go into any operational radar in the future. So we're not. It's not our highest priority to just push the data quality to the extreme positive limit. So just as a word of warning, all of these radars are within 50 kilometers of each other. So these 3 radars here, our research radars, are in the direct vicinity of Helsinki, which is down here. And the Wichti radar is about 40 kilometers up here, a bit to the north. So they're all very close to each other. So they are, when I compare data, which I'm not showing here, but I have done that as well. When I compare data from different radars, then they're typically looking at the same area. And if you compare the lowest elevation angles, then they usually are not so different in observation height either. So these are the example for the input observations. So this is now again an observation from Wichti radar, and this rho HV is cross correlation is an assessed observable, and so is phi dp. So these are the 2 core observables I'm assessing. Then ZER is going in as a selection criterion, but also can be assessed, looking for the ZER calibration from the data, while ZH is typically only used for data selection, so selecting data between 10 and 20 dB set or 20 and 40 dB set or whatever you decide. And so this is again from Wichty radar. Again, this is the log normal fit for ROHV. And again, the contribution of all observations below ROHV equals 0.96 is again less in the order of 10% or less. And this is now phi-dp. And what is obvious here is really this kind of even for ZH between 10 and 20, you have this kind of tail here. And of course, unlike ROHV, where that is really an observation that is more or less depending on the range cell you're looking into, phi-dp, of course, even if you're restricted to 10 to 20 dBz, data might come from an area where you have passed much higher dBz before you get there. So this is one weakness in the current method, which of course could be ironed out with more effort. Just select data that have not passed through higher ZH values or radar reflectivity ranges with higher radar reflectivity value. But still, this gives a pretty good indication on the width of the distribution of the phi-dp distribution in the areas where you have low ZH and you should not have a massive shift in phi-dp, which I will show later in a direct comparison. There are cases where you can see very clear differences here. And this is the same then for the Kumpula weather radar, which is our C-band solid state amplifier radar at the physics building of Helsinki University. And again, you see this ROHV here, pretty narrow, pretty low value here. So in this case, the contribution of lower ZH, of lower ROHV values is a bit higher, but in this case, it's due to the weather, because if you look at the plot here, which gives the ZH image at this point, and look at the light blue ring, which is the melting layer height, there are some cells here which have higher backscatter or higher radar reflectivity, and that of course affects the ROHV adversely. So that is a weather situation that was not absolutely optimal for assessing the data quality, but it was the only one of this radar I had available at the time or at the moment. And looking at the ROHV, and interestingly, the phi-dp, interestingly here, this tail here, which we have seen from Kumpula radar, is missing. But again, this is a different weather situation. So always be aware that the weather you are observing, of course, to some degree affects the results you're seeing. And so that's always something that one needs to keep in mind. So then, looking at the ZTR calibration, so our weather radar, research weather radar at Kerala has recently been upgraded with a new magnetron, a completely new type of magnetron, which we are introducing, more modern, up-to-date design compared to the older ones. The problem here is we are not allowed to run bird bath calibrations because we are something like 8 kilometers away from Helsinki airport, and these are the main runways. So either in approach or in start, the aircraft are passing very close over the weather radar, which is on a water tower here in Kerala. So bird bath scan is out of the question, not allowed, period. So what do we do when we want to adjust our radar? So what we have done after the new magnetron went in, of course, a kind of coarse calibration has been done. And so we ended up with something like 0.8 as the difference in this assessment here. So based on this, we have done a first adjustment, which now put us into plus minus or between 0.1 and 0.2. We then can do this repetitively again based on this new data until we are in the right place. But that's currently the only non-invasive method that allows us to monitor ZTR and adjust ZTR in the operation without kind of climbing up the tower and doing hardware-related work. And the general data quality, so I have data from last autumn with the old magnetron here, and this is situation with a new magnetron just 2 weeks ago now, or 3 weeks ago. And the point is, even though this weather system here is much more extensive than in this case, the range of the melting layer height is pretty much the same. So the data going into the assessment are relatively the same. And this is the difference in ρHV. So you clearly see the new magnetron provides a much more narrow distribution, much less contribution from values below 0.96. The only thing we're not yet quite happy with is that our location here has shifted a little bit to the left. So it eventually should go right to the right of this place here again, and improve over the old magnetron, which, by the way, it's that bad because it has been run well beyond its best before date. So that has been run ages over the expected lifetime. It still worked okay-ish. And again, this is a weather radar used for testing methods and for research. So we never cared too much about the data quality. But of course, we are very happy that the new magnetron clearly has improved the situation here, and we will fine-tune it a bit more to improve the peak here further. But at the moment, this is not our highest priority. And then again, looking at the phi-dp, so again, the weather situation pretty similar. The phi-dp here much more narrow with the new magnetron. So obviously, this very wide distribution here is due to the bad quality and the bad phase phase stability of the old magnetron before it was replaced. So that again, not unexpected because it was operated much, much longer than its expected lifetime. So conclusions. So I have demonstrated this idea, this method with statistics that have been created using Python code, and we found it very useful for monitoring and adjusting our ZTR calibration in the absence of other methods and other opportunities. And we clearly have managed to improve our ZTR calibration. And so we propose that this is a valued tool for monitoring ZTR calibration in an operational setting as a kind of everyday monitoring opportunity. Also, there have been very clear indications on the difference of weather radar data quality here shown in the difference between the old and the new magnetron of our Caravan radar. The width of distribution, the cumulative contribution of ρHV less than 0.96 are good indicators for ρHV. And for phi-dp, mainly the width of the distribution is an indicator, which is indicated in the fit by the stretch factor. So the more the horizontal axis can be stretched, the more narrow is the resulting distribution in the real phi-dp, on the real phi-dp axis, and the gamma parameter of the distribution is a good indicator. If that gets very small, then the distribution is also very wide and the quality is not great. So what can be done, of course, in the future, rather than just using one scan, this could be extended to multiple scans, collecting data from maybe even continuously, sliding a week or months or whatever, whenever there are observations available that fit the bill. That would allow for much lower sample size and for even more stringent restrictions in ZH or ZTR. Of course, it would be possible to develop an automated tool that could also ingest external observations, like, let's say, temperature measurements, radio sound launches, or whatever. If you have radar bus systems available that give you the melting layer height in the atmosphere, could be ingested. Of course, it also would be possible to apply weather radar internal observations or products like hydroclass. Only use range cells where your hydroclass gives you liquid precipitation, exclude all other kinds of observations, or directly use polarimetric observables and do your hydroclass processing even in the tool would be possible. And of course, looking into adaptive calibration and maintenance. So rather than doing this on a fixed schedule, only do it when it's possible, but also do it when it's necessary, even before your regular maintenance schedule. So yeah, that's effectively what I wanted to show. So I have shown that the method works. I've demonstrated with the Python code written for that, and we have clear indications that it works for the data quality, that it allows comparison and assessment, and it also has allowed us to adjust the ZDR calibration in the absence of any other method possible. And so it could be extended by statistics over multiple scans, which allow for a larger sample size. Could be used to develop automated tools, ingest external observations, ingest more observations from the radar itself, and allow for adaptive maintenance or calibration schedules rather than fixed ones. And of course, everybody, as already mentioned, everybody talks about artificial intelligence, machine learning nowadays. It could be supplemented, but actually I found that generic intelligence also helps a lot to with assessing these data already. Thank you for your attention.
Ask you talking about October when you compare old magnetron and new magnetron.
So let me go back.
And not the
next one, yeah.
There seems to be the old magnetron some saturation at 1, and I wonder whether you have some explanation for this.
Actually, I don't really know. As I said, at this point, this magnetron was already very well beyond his best before date. So I have no idea if this is an artifact that really has been created by the magnetron itself, if it's kind of creating weird output that shows or that creates this one maximum. It's definitely something I didn't find with our solid state radars, and I didn't find with the new magnetron. So this might really be down to the magnetron itself and its aging behavior, but that's a bit beyond my current expertise. So I have not really looked into what the magnetron might do to create this saturation at 1. But it might be, as you said, it might be something like a saturation effect, that it simply occasionally puts signals out that are so bad or so saturated, or it's kind of occasionally missing, let's say, missing a beam, going into saturation for a single beam or something like that could create something like this. But again, that's purely speculative. I really don't know how these magnetrons behave when they get very old. Maybe, by the way, someone in the room has an idea.
This slide. So I think a possible explanation might be that the magnetron is doing for shift in frequency, and maybe the rest of the radar system is not following the frequency. Hence we get a phase shift. But I'm just guessing.
Yeah, again, it's this at this stage the magnetron was very old, so I would definitely think this is an option, or what might have happened occasionally.
Thank you for the talk. Do you think you have some range effect with the distribution of the rotary, for example? You used over the whole range?
No, actually, if you go back, in this case, as I said, even though the weather system, when I looked at the new magnetron, was more extensive, interestingly, the melting layer height and as such, the range up to melting layer height was pretty much the same. So I'm looking more or less at the same ranges in both cases here. The only difference is that there is this area with a higher ZTR here in the ranges up to melting layer height, while here there are a few spots as well, but not so extensive as here. So that might be one contribution, but I believe that in general this distribution is definitely dominated by the behavior of the magnetron, not by the slight differences in the weather situation at this point in time, or the 2 points in time.